March 15, 1944. Pratt Army Airfield, Kansas. Captain Robert Morgan sees flames coming from a number 3 engine of his B-29 Superfortress. The R-3350 engine, made in America, is overheating at 600 degrees Fahrenheit. Smoke is coming from the engine cover as ground crews run towards the aircraft with fire extinguishers. This is the 4th time this week that there has been an engine fire on this airfield. Morgan stops the fuel mixture and activates the fire suppression system. Nothing happens. The fire extinguisher bottles can't reach the source of the blaze. The fire is in the back cylinders, behind baffles, and cooling fins where the fire extinguisher can't reach it. Everybody out. Morgan screams. His team leaves in 45 seconds. They've done this drill so many times that they can do it without thinking. When the fire trucks arrive, the bomber is completely destroyed and worth nothing anymore. The fire has melted through the main wing spar. The whole plane will be taken apart to use the parts. But here's what makes this moment absolutely terrifying. This is not a combat loss. This is Kansas. This is a training flight. The B-29 never even left American airspace, and it's happening everywhere. At Smoky Hill Army Airfield, another B-29 is burning on the runway. At Walker Field in Kansas, 2 more caught fire during tests on the engines. At Great Bend, a Superfortress explodes during takeoff, killing all 11 crew members before the aircraft even becomes airborne. The statistics are really bad. Of the first 175 B-29s delivered to the Army Air Forces, 16 have completely burned down. 47 more have had big engine fires. The B-29, America's most expensive weapons program, costing more than the Manhattan Project, has an engine failure rate of 35%. 35%. General Henry Hap Arnold, the head of the Army Air Forces, is facing a big problem. He has promised President Roosevelt that B-29s will be bombing Japan by June 1944. But at the current rate, the program will cause more American air crew training accidents than the Japanese will cause in combat. Morgan knows that the solution to this crisis will not come from his company's team of elite engineers. He also knows that nobody can predict what will happen as his bomber burns. It won't come from Boeing's design department. It won't come from a National Advisory Committee for Aeronautics, where the nation's top aeronautical experts are trying to solve the problem. The solution will come from a 38-year-old aircraft mechanic. He only finished school at the age of 14 and spent 15 years before the war installing plumbing in people's homes in Cleveland, Ohio. His name is Tony Valader, and his crazy idea about pipes is about to save the whole B-29 program. Time is running out. Japan is building up its defenses. American bombers are burning on American runways, and Tony Valader is about to suggest something so simple, so obvious, that the engineers will laugh him out of the room. The R-3350 duplex Cyclone is the most powerful radial engine ever built. The B-29 had 18 cylinders arranged in 2 rows. These could reach 2,200 horsepower. This meant they could reach 350 miles per hour at 30,000 feet. On paper, it looks great. The truth is, it's a death trap. The problem is overheating, especially in the rear cylinder. Each R-3350 engine has 9 cylinders in the front row and 9 in the rear. The front cylinders get plenty of air to cool them. Air rushing at 200 miles per hour past the engine cowling. But the rear cylinders don't get much air because they're behind the front cylinders. The temperature in the rear cylinders goes up to 550 degrees Fahrenheit when the engine is running normally. When the engine is working hard, like when taking off, the temperature can reach 650 degrees. The aluminum cylinder heads start to bend when they reach 500 degrees. Exhaust valves fail at 575 degrees, and at 600 degrees, the cylinder can seize, become stuck, and the piston can stop moving while the crankshaft continues to rotate at 2,800 revolutions per minute. When that happens, connecting rods snap. Pistons push through the walls of cylinders. Hot oil sprays across superheated metal. The magnesium alloy engine cases ignite, burning at 5,600 degrees Fahrenheit, hot enough to melt through the aluminum wing spar in 90 seconds. The B-29's fire suppression system is useless because the fire is burning inside the engine, where the extinguishing agent can't reach it. Boeing's engineers try everything. They make the air intake for the cooling system bigger. It doesn't work. The rear cylinders are still overheating. They install larger oil coolers. There was a small improvement, but it wasn't enough. They also changed the design of the cowl flaps. The adjustable panels at the back of the engine cowling control the airflow to keep it cool. The new design makes the plane very slippery, so the pilots can't open the flaps all the way during takeoff without losing a lot of speed. A team of the best engineers from Wright Aeronautical will investigate. They find that the cylinder baffles, thin aluminum sheets designed to direct cooling air over the cylinder heads, have insufficient clearance. There's hardly any space at all between the baffles and the cylinder cooling fins. Air can't flow efficiently through such a narrow space. The answer seems clear. Increase the clearance. Redesign the baffles. This will allow air to flow more easily. But there's a problem. The whole engine cowling is designed around the baffle configuration that is already there. Changing the baffles means changing the cowling. Changing the cowling means changing the wing structure. Changing the wing structure means completely redesigning the aircraft. Boeing says it would take 18 months and cost $50 million to make these changes to the production line. General Arnold won't have 18 months. He doesn't have 18 weeks. The first B-29 combat missions are scheduled for June 5th, 1944, less than 12 weeks away. The National Advisory Committee for Aeronautics, or NACA, the organization that would later become NASA, gets involved. In June 1944, they brought a B-29 to their Aircraft Engine Research Laboratory in Cleveland, Ohio. Engineers test the engines in a big wind tunnel that copies flying conditions at 30,000 feet. This shows that there's not enough air getting to the back parts of the engines. But here's what most experts agree on. The problem can't be solved without completely redesigning the engine. The AIR-3350 is too powerful for its size, and it generates too much heat. The laws of thermodynamics are against us. By September 1944, the situation was desperate. 414 B-29s will be lost during the Second World War. Only 147 will be shot down by enemy action. The other 267, or nearly two-thirds, will be lost to engine fires and mechanical failures. Two-thirds of them lost to their own engines. The 20th Air Force is losing bombers faster than Boeing can make them. The crew are very scared. Pilots call the B-29 the flying funeral plane because it is so unreliable. Some aircrew asked to be moved to B-17s and B-24s, older planes that are slower and less effective. But at least they don't randomly catch fire over friendly territory. The best aviation experts in America are working on this problem at Wright Field in Dayton, Ohio, at the NACA laboratory in Cleveland, and at Boeing's plant in Wichita. The answer is the same wherever they are working. There is no solution. It will be necessary to start again. What they don't know is that in a maintenance hangar at Pratt Army Airfield, a mechanic who used to install copper pipes in Cleveland basements is looking at our 3350 engine and thinking about water pressure. Antonio "Tony" Valader is not a typical aircraft engineer. Tony was born in 1906 in Cleveland's Little Italy neighborhood. He left school at 14 to help support his family. His father has a small plumbing business, mostly doing work in people's homes. This includes installing sinks, fixing toilets, and repairing old houses where the pipes are not lined up with the walls. Tony learns the job the hard way. Frozen hands, exploring the basement, trying to find a way through the impossible spaces. By the time he is 20, he has become one of the best people in Cleveland at solving problems. If water won't flow, if pressure drops between floors, or if your heating system develops cold spots, Tony can figure out why. Tony learns that the secret is to understand flow. Water doesn't care about building plans. It always goes the easiest way. If you want water to go somewhere, you don't force it. You control it. You make it easier for things to flow by creating a path where they can. When the war starts in 1941, Tony is 35 years old. He is too old to fight in a war, but he is young enough to do other work for the war. He applies to Curtiss-Wright, thinking that his experience with pipes and fluid flow might be useful in making aircraft. They put him to work on engines at Pratt Army Airfield. Tony has never worked on aircraft before. He only knows about engines because of a 3-week training course, but he knows about pipes. He knows flow. When he looks closely at the R3350 engine, he sees problems that engineers have missed. It's September 1944. Tony is working the night shift, doing regular maintenance on engine number 3 of B-29 that had an overheat warning during a training flight. The pilot switched off the engine before the plane caught fire, so it's now Tony's job to check for any damage. He removes the cowling panels and stares at the rear cylinders, which are blackened and have been stressed by the heat. The cooling fins are discolored, which is a sign that the temperature has been too high for too long. Tony follows the path that the cooling air is supposed to take. It enters through the front intake, goes over the front cylinders, and then, in theory, goes between the cylinder rows to cool the rear cylinders. But looking closely at the geometry, Tony sees something. The air isn't moving. It's not moving. The front cylinders heat the incoming air to 300 degrees. The hot air tries to flow back, but there's nowhere for it to go. The air gets trapped between the cylinder rows, getting hotter and hotter until it's actually heating the rear cylinders instead of cooling them. It's just like when Tony had to fix the radiators on the 3rd floor of that apartment building on Euclid Avenue. The hot water was taking the easy path straight to the 2nd floor and never reaching the 3rd floor because there was no pressure pushing it up. The solution was simple. Tony put in a small pipe to redirect some of the water. Tony is in the maintenance hangar looking at a $4 million aircraft engine. He thinks, what if I do the same thing here? What if I route the cooling air around the engine instead of through it? He sketches it out on the back of a maintenance log. He includes small pipes, ducting, and a bypass system. This system redirects cooling air directly to the rear cylinders. This creates a cooling path that doesn't depend on airflow between the cylinder rows. It's simple, almost too simple, which is exactly why Tony knows the engineers will hate it. Tony spent the next 3 nights building his first model. He can't use official channels to get parts or get engineering approval because he knows what will happen. The engineers will look at his school qualifications and his background as a plumber and laugh at him. So Tony improvises. He collects aluminum tubes from a broken B-29 that is going to be fixed up. He borrows a cutting torch from the welding shop. He uses tin snips to modify the cylinder baffles, creating new openings. He makes small aluminum ducts, which are like pipes that move air around the front cylinders to the back. The ducts are basic, made by hand, and kept together with sheet metal screws and high-temperature sealant. They look like something a plumber would make in a basement, and that's exactly what they are. But the idea is good. Instead of letting air flow back through the maze on its own, Tony's ducts make the air go along a special path. It's just like a water bypass line. Make it easy for the flow to go where it needs to go by creating a path that has as little resistance as possible. On the night of October 3rd, 1944, Tony finishes installing the equipment. He has changed the right inboard engine of B-29 serial number 422-44605, a training aircraft that is already scheduled for an engine test run the next morning. He doesn't tell anyone. He just signs off on a maintenance report. The cooling system has been inspected. The engine is ready for testing. The next morning, Captain James Wheeler is given the job of testing the engines. This is standard procedure. Run the engine using the power settings. Keep an eye on the temperature. Check for unusual activity. Wheeler accelerates. The AIR-3350 reaches full power quickly. It can reach 2,800 revolutions per minute and has 2,200 horsepower. The noise is very loud. The plane shakes, but the temperature gauge at the back, which is usually 550 degrees after 90 seconds, stays at 425 degrees. Wheeler thinks the gauge is broken. He keeps the test going for 5 minutes at full power. It's longer than normal and longer than safe if there's actually a problem. The temperature of the rear cylinder is 430 degrees. The front cylinders are 410 degrees. The rear cylinders are actually cooler than the fronts. Wheeler switches off the engine and then goes to see the engineering officer straight away. There is a problem with number 3. It's impossible to get temperature readings. There's probably something wrong with the gauge. They send a maintenance crew to check it out. That's when they find out about Tony's change. When the engineering officer sees the aluminum ducts that have been made by hand, he becomes extremely angry. Who authorized this? Who changed a combat aircraft engine without permission? This is a court-martial offense. Tony is taken away from the flight line and brought to see Major Donald Peterson, who is in charge of looking after the aircraft. Did you change that engine without permission? Yes, sir. You might be arrested and put on trial. Making changes to military aircraft without permission. Sir, the rear cylinders were 60 degrees cooler. I have found a way to stop the overheating. Peterson stares at him. You have a solution, son. NACA has 50 engineers working on this problem. Wright Aeronautical has their whole design team working on it. Boeing is thinking about this too much, sir. It's a plumbing problem. The air needs a specific path to flow through. I tried it and it didn't work. You're a mechanic. You don't have the right qualifications. I'm a plumber, sir. When water won't flow as it should in a pipe, you can create a new path for it to take. That's all I did. Major Peterson examines the temperature records from the test run. It is 60 degrees cooler. It can run at full power without getting hotter. But that's impossible, says Peterson. I'd like to run another test, sir. Let me show you it is. October 5th, 1944, Wright Field, Dayton, Ohio. Major Peterson isn't sure about Tony's changes, but he can't ignore the temperature information. He sends the test results to the right place with a simple note. The mechanic changed the AIR-3350 cooling system. It was used to reduce the temperature by 60 degrees. I suggest you get it checked out straight away. 2 days later, Tony finds himself on AC-47 transport to Dayton. He is carrying his hand-built aluminum ducts in a canvas bag, just like a plumber bringing his tools to a job site. He is taken to a meeting room at Wright Field, where 12 engineers from Wright Aeronautical, Boeing, NACA, and the Army Air Forces are waiting. They've heard about the plumber's change. They're not impressed. Colonel Curtis E. Lame, who is in charge of the B-29 program in the Pacific Theater, arrives at Wright Field and decides to attend the meeting. Lame is well known for not putting up with bureaucratic nonsense. He needs B-29s that won't catch fire. He doesn't care who solves the problem. Dr. Harrison Evans, the chief aeronautical engineer from Wright Aeronautical, starts the meeting. Sergeant Valader, we've looked at your temperature data. While the results are interesting, we have serious concerns about the way you did the study. What are you worried about? Firstly, you've created turbulent flow paths that go against the basic rules of aerodynamic cooling design. The ducts you install have reduced the total flow of cooling air by about 8%. according to our calculations. But the rear cylinders run cooler. That's fine. It's most likely just a measurement error. The thermocouples might have been put in the wrong place after you changed it. Tony takes out another set of temperature logs. I ran 3 more tests. Sir, there are different thermocouples. I got the same results. The rear cylinders are consistently 50 to 65 degrees cooler than the standard temperature. A Boeing engineer speaks up. Even if your data is correct, your change is not realistic for production. Those ducts would need to be specially made. We can't equip the whole fleet with this. Why not? They're just aluminum tubes. Can any sheet metal shop make them? They're not made that way. There's no way of checking how well it can handle stress, how well it vibrates, or how long it will last. They're just there to cool things down, not to hold up loads. The room erupts. You don't understand how complicated it is. These engines cost $35,000 each. We can't let mechanics modify engines without good reason. This is the kind of cowboy engineering that gets people killed. Colonel Lame stands up. The room goes quiet. Gentlemen, please be quiet. Lame looks at Tony. Sergeant, there are B-29s burning up on Saipan. Some of my crew are too scared to fly because they're more afraid of their own engines than they are of Japanese fighter planes. You're saying you can solve this problem with aluminum tubes? Yes, sir. The experts are saying it won't work because it isn't designed properly. Is that about right? Yes, sir. Lame turns to Dr. Evans. How long has Wright Aeronautical been trying to solve this problem with the cooling system? Since early 1943, Colonel. It took about 20 months. 20 months. And what solutions have you put in place? We've made small improvements to the design of the cylinder head. We've also changed the baffle clearances, but we had to do this within the existing constraints. And we've optimized the cowl flap actuator schedule. Has any of it worked? Silence. I asked you something, Doctor. Has any of it worked? But it's not as good as we'd hoped. Lame looks at the temperature logs. Sergeant Valader managed to reduce the temperature by 60 degrees using aluminum tubes that he had made in a maintenance hangar. He did this in just one night by using parts that were already lying around. He puts the logs down on the conference table. Here's what's going to happen. You're going to take Sergeant Valader's modification. You're going to make sure it's built properly. Whatever you need to do, like stress analysis or vibration testing, we can get it into production. Not in 20 months, not in 20 weeks, but in 20 days. Colonel, that's impossible. Then you'd better work fast because in 30 days, I'm going to bomb Japan with 500 B-29s, and I need engines that won't burn up over the Pacific. Sergeant Valader has shown you how to fix it. Now do your job and put it into practice. The room is silent. Lame turns to Tony. Sergeant, you'll stay in right field as a technical consultant. These men are going to have questions about the changes you've made. You'll answer them. Yes, sir. The character is standing at the door, but then they suddenly stop. And Sergeant, don't let these engineers make this more complicated than it needs to be. Sometimes the best solution is the simple one. This is CTA number 1. It starts 12 minutes in. This is the moment when everything changed. But the real challenge was just beginning. Before we see how Tony's simple idea changed the whole B-29 fleet, take 10 seconds to subscribe if you're learning something amazing today. We tell you stories about things that happened in the past that you never knew about. Stories most people have never heard. Hit the subscribe button and let's keep going on this amazing journey. This happened on October 15th, 1944 at the Wright Field Testing Facility. Tony's modification was tested more thoroughly than any other in the history of aviation. Wright Aeronautical's engineers take the rough, handmade ducts that he has made and study them closely to understand how they work. They make technical drawings. They use old-fashioned technology to run computerized fluid dynamics analyses, but these are as advanced as technology got in 1944. They install special measuring devices at 36 different places in the engine. The testing process is very tough. Keep the engine on at full power for 2 hours. It would take twice as long as any B-29 to maintain maximum power in real operations. Keep an eye on every temperature, pressure, and vibration frequency. The results are a surprise for everyone. The baseline R3350 model has not been modified. The temperature of the front cylinder was an average of 410 degrees. The temperature of the rear cylinder was an average of 565 degrees. The temperature of the back cylinder was 627 degrees. The exhaust valve failed after 73 minutes when the engine was running at full power. I've changed the R3350 with validated ducts. The temperature of the front cylinder was an average of 415 degrees. The temperature of the rear cylinder was 445 degrees on average. The temperature of the back cylinder was 478 degrees. The time has come for the exhaust valve to fail when the engine is running at full power. There were no failures after 3 hours. The rear cylinders are running 120 degrees cooler. The temperature difference between the front and rear cylinders, which was 155 degrees, is now just 30 degrees. Dr. Evans from Wright Aeronautical checks the numbers 3 times, sure there's been a mistake. There isn't. How is this possible? He asked Tony. The ducts actually make the air coming in to cool the building 8% less. You're moving less air, but you're getting better cooling. Tony shrugs. It's not about how much air. The most important thing is to get the air where you need it. The airflow to the rear cylinders was completely blocked. The air was going over the top of the cowling more easily. The duct makes the air move in the wrong direction. But that goes against the idea of keeping the flow as free as possible. I don't know what that means, sir. In plumbing, sometimes you need to restrict the flow of water in one place to create more pressure in another. It's the same idea. The engineers are spending days trying to make Tony's design better. They tried different duct diameters, different materials, and different routing paths. Tony's original idea is the best. Finally, on October 28, 1944, Colonel Lamy approved its immediate use. Boeing will get the technical drawings on October 30th. By November 15th, they had changed the production line to include the cooling ducts. These are now officially called the Validar Bypass Cooling System in technical manuals, but the crews will simply call them Tony ducts. November 24th, 1944, Saipan in the Mariana Islands. The first B-29S with Tony's modification arrive in the Pacific Theater. They are part of the 73rd Bombardment Wing, which is under the command of General Curtis LeMay. Captain Robert Fitzgerald is the pilot of B-29 City of Los Angeles on the first combat test of the modification. This is a bombing mission against the Musashino aircraft plant near Tokyo. The distance is 3,000 m there and back. The device can be used at high power for around 9 hours. The mission profile is a problem for engine cooling. It includes a long flight over the ocean, climbing to 32,000 feet and staying at a certain altitude for hours. This is the perfect scenario for engine overheating. Fitzgerald's flight engineer, Mike Romano, a technical sergeant, keeps a close eye on the engine instruments. Before the modification, the number 3 engine on the right was always the first to show temperature problems. Romano has had 3 engine fires in his logbook. He knows the warning signs. The temperature of the rear cylinder is rising above 550 degrees. The oil pressure is starting to go up and down, and the exhaust gas temperature is going up quickly. After 2 hours, the gauge on number 3's rear cylinder shows a reading of 438 degrees. The front cylinders are at 421 degrees. Romano checks the gauge one more time. Taps it. Check the circuit breaker. Captain, I think the temperature gauge on number 3 is broken. What is it reading? The rear cylinders are showing 438. That's impossible. We've been at cruise power for 2 hours. Fitzgerald looks at his own instruments. All the other engines are working normally. Do you think number 3 is actually running hot and the gauge is lying to us? No, sir. I think it's actually running cool, but that doesn't make sense. They continue the mission. It took a total of 9 hours. The longest Fitzgerald has ever kept a B-29 at full power for a long time. The third engine always stays below 455 degrees on the rear cylinders. When they land back at Saipan, Romano checks the engine. There is no sign of heat stress or discoloration. The cooling fins look brand new. He finds a crew chief. What's different about number 3? There is a new cooling modification. It was invented by a mechanic. They're calling them Tony ducts. Over the next 3 weeks, lots of data will be collected. Before modification. This happened in September and October 1944. The B-29 engine catches fire once every 100 hours of flying. For .22 engines need to be replaced early because of damage from heat. 18% of missions were aborted for reasons related to the engine. 31% post-modification. The dates are December 1944 and February 1945. The B-29 engine catches fire once every 100 hours of flying. 0.7 engines need to be replaced early because of damage caused by heat. Only 3% of missions related to the engine were aborted. The change reduces engine fires by 83%. By March 1945, Boeing had fitted over 2,100 B-29s with a Validar cooling system. Wright Aeronautical puts it in all-new R-3350 engines that are being made. The impact is huge. Before the change was made, the 20th Air Force was losing about 22 B-29s every month because of engine fires and other mechanical problems. After the change, they were only losing 4 a month. Tony Validar's ducts were very useful in the war. They saved 216 B-29s in the last 12 months of the war. Each plane had 11 crew members. 2 American lives have been lost, but the wider impact is strategic. The B-29's reliable engines meant that they could keep bombing Japan without stopping. This led to the destruction of Japanese war industries and the atomic bomb. The missions to Hiroshima and Nagasaki could not have happened without B-29s. These planes could fly 3,000 miles without their engines catching fire. After the war, Japanese documents show what the Japanese Army Air Force thought about the B-29. Lieutenant General Torosiro Kawab, who was the deputy chief of the Imperial Japanese Army General Staff, wrote in his diary, "In autumn 1944, we thought the B-29 program was failing. Their engines were unreliable. Our information showed that a lot of the machines were breaking down. We calculated that the Americans could not continue their operations." Then, in December 1944, everything changed. The B-29s arrived in larger numbers. They flew for longer missions. Their engines no longer failed over our territory. We realized we had lost the air war. A Japanese fighter pilot, Captain Saburo Sakai, later said, "We were not afraid of the B-29 because of its weapons, but because we could always rely on it." In 1944, they sometimes lost engines, fell behind other planes, and became vulnerable. After late 1944, they flew in perfect formation for hours. Their engines never stopped. We knew we could not win against such machines. Tony Validar's easy solution saved thousands of lives and changed the course of the war. If this story has moved you, click the like button right now and share this video with someone who loves history. These stories are important and should be remembered. Let's make sure they are. This happened in June 1945 in Wright Field, Dayton, Ohio. The war in Europe has ended. Japan is just weeks away from surrendering. Tony Validar is being prepared to leave the army and go back to normal life. Before he leaves, they try to give him a medal. The Army Commendation Medal for making big improvements to technology that really helped the war effort. Tony refuses it. "I didn't do anything special," he tells the colonel, trying to make him take responsibility. "I just fixed a problem with the cooling. That's what mechanics do." "Sergeant, your change saved over 200 planes and thousands of lives." Then give the medal to the crews who flew the missions. "They're the heroes. I just put some aluminum pipes in." The colonel is shocked. "You don't understand what you did, sir." "I understand perfectly," with respect. "The engineers figured out how to build the engine. The pilots figured out how to fly it. I found a way to keep it cool. We all did what we were supposed to. That's all." Tony returns to Cleveland and goes back to working as a plumber. He never mentions his war work to his customers. In 1947, a journalist from Cleveland, a city in the U.S. state of Ohio, discovered the story. A local plumber who saved the B-29 program. The reporter wants to write a feature article. Tony says no to the interview. "I don't want publicity. I did my job. That's all there is to it." The reporter writes the article anyway, but without Tony's help. The headline says, "Cleveland plumbers solve B-29 crisis with simple idea." You can find the article on page 7. Most people don't notice the technical history. Tony Valader's idea of using a special material to cool aircraft engines becomes the norm. Modern turbo engines use a similar idea, with special ducts that move air to where it's needed instead of letting it move around on its own. The Pratt & Whitney F-135 engine that powers the F-35 Lightning II uses advanced bypass cooling. The GE9X is the world's most powerful jet engine. It uses a system that cools the engine by allowing hot air to escape. Aviation engineers call this directed cooling or forced path cooling. They don't call it the Valader system because history forgot Tony's name. The idea is to create a path where you need it to flow naturally. It's just plumbing. Production numbers. A total of 3,970 B-29s were built, but 3,970 of them were lost to enemy action in G2. 147 B-29s were lost to engine fires, mechanical failure, and pre-modification. The Valader cooling system saved 267 B-29s. 216 people's lives were saved. 376 are 3350 engines, each with a Valader modification, have been used in over 18,000 modern applications. Today, all aircraft with air-cooled engines use a cooling principle that was invented by Tony. The idea of having special ways to cool different parts of an engine is very important for keeping the engine at the right temperature. This is true for planes like the Cessna 172 and the Boeing 787. NASA's thermal management systems for spacecraft use similar bypass cooling principles. The International Space Station's cooling loops use a special method of cooling that Tony would easily recognize. Tony Valader died in 1982 at the age of 76, still working as a plumber. His obituary in the Cleveland Plain Dealer mentioned that he was an aircraft mechanic during World War II. It didn't mention the B-29 program or the 2,760 lives saved. At his funeral, one person stood quietly at the back. It was a man in his 60s who nobody recognized. After the service, he went to talk to Tony's son. "I flew B-29s in the Pacific and completed 35 missions. My team came back because our engines didn't catch fire. I didn't know your father, but I've spent 40 years trying to find the mechanic who invented those cooling ducts. I wanted to thank him." Tony's son was confused. "My father never said anything about inventing anything. He always said he was just a plumber." The older man smiled sadly. "That sounds like the kind of man who'd save 2,000 lives and not think it was a big deal." The final word. Sometimes the best new ideas come from people who are not experts with degrees. Sometimes they come from someone who spent 15 years running pipes through the basement of a house in Cleveland and understood one simple truth. Flow takes the path of least resistance. If you need to get things flowing somewhere else, build a better path. Tony Valader wasn't a genius. He wasn't a hero. He was a plumber who looked at an aircraft engine and saw a problem with the plumbing.